This is Mr. Hardesty. We're going to solve a real-world example by finding the line of best fit for the data that we have. The table shows the percent of U.S. workers in farm occupations. The years are calculated since 1900, starting at 0 and adding 20 years, 40 years, 60 years, 80 years, and 94 years. The corresponding percentage of farm workers is 37.5, 27, 17.4, 6.1, 2.7, and 2.5. Let's draw a scatter plot and determine what relationship exists, if any, in the data. First, let's call the years x, and that will represent our independent variable. Those will be represented across the x-axis. We'll call the farm workers y. That's our dependent variable, and we'll calculate that up the y-axis. We'll plot the information as ordered pairs, beginning with 0, 37.5, and plot that right on the y-axis. 20, 27 is the next ordered pair. 40, 17.4. 60, 6.1. 80, 2.7. And finally 94, 2.5. Now let's determine if a relationship exists, and clearly there is one. As the number of years increases, the percent of the farm workers decreases. That is a negative correlation between x and y. In part B, we'll draw a line of fit for the scatter plot that we created in part A. To do that, project at the first point or close to it and draw the best line that we can that comes close to containing as many of those points as possible. That is the best fit line that we can get between our 6 ordered pairs. In part C, we'll write the slope-intercept form of the equation for the line of fit. Slope-intercept form is y equals mx plus b, where we need to represent both the slope, which is m, and b, the y-intercept. First, let's calculate slope. The equation for the slope is the difference of the y's over the difference of the x's. And that'll work for any points on the line. We're going to use 2 points that have come out nicely when we drew this line, or actually the second line that was sketched with this example. And those ordered pairs are 20, 27 and 94, 2.5. So we'll use those as our ordered pairs and plug those into the slope formula. The difference of the y's will be 27 minus 2.5, and we'll subtract the x's in the same order. That's 20 minus 94. When we do the math, we get 24.5 for our numerator and negative 74 for our denominator, which is not a very attractive fraction. Let's double that and multiply that by 2, so that'll give us 49 for our numerator and 148 for our denominator. And technically that's a negative 148. We know that the whole value is negative for the slope, and that's m. We'll plug that into our original equation, y equals mx plus b. Let's take and put that slope in for m. And so now we'll write y equals negative 49 148 times x plus b. To solve for b, we're going to take and plug in a point for x, y. It can be any of those points on the line. We'll pick one that we've already used here, 20, 27. That's x, y. We'll place 20 in for x and 27 in for y. and then our variable, our missing piece, will be the y-intercept, which is b. So we have 27 going in for y. Our slope will rewrite and multiply that by 20, the x value of one of the ordered pairs, plus b. We'll do the multiplication and have 27 set equal to negative 245/37 plus b. And finally, to get b by itself, let's add 245/37 to both sides. And b is equal to 1,244/37. We were to write the slope-intercept form equation. That was our directive, and we can do that now by plugging in the slope for m and our fraction that we found for b. So our final answer is y equals negative 49/148 plus 1,244/37 for b.